What's up? I'm Vin, and today I want to show how to find the interval of convergence of a power series. Now, these are just some definitions that we're going to need to know, and the way I like to visualize these definitions is that, first off, the center of a power series is the x value that makes all the terms zero. And then how I imagine this is that the radius of convergence starts at the center and it goes either to the right, a distance of r, or it goes to the left, a distance of r. And that distance left and right helps you build the interval of convergence, and it's going to go from c minus the radius to c plus the radius. And just know one part of the process is that we have to check the endpoints to see if that's going to give us, if it's going to be a part of the complete interval of x values that create a convergent series. But we'll warm up with 3 quick examples. So let's say we want to find the center of each power series. Well, remember the definition. The center is the x value that makes all terms equal to 0. So what I'm imagining in my head is, when is x minus 3 equal to 0? And that little bit of algebra you could do in your head, and that would tell us the center of this power series is at 3. If we look at the next one here, we could just think real quick, the inside expression, x plus 5 over 2, when is this equal to 0? That's the $1,000,000 question. And the center of this series would be at -5. So if we throw something a little bit more complicated this way, now we're just thinking, when is the inside expression 2x minus 1 over 3 equal to 0? And if you do that algebra, that's going to tell you the center of this third power series is going to be at 1/2. So just know, when you want to find the radius and interval of convergence for a power series, you have to use the ratio test. This is a $1,000,000 test for you to know. And just know there are 3 cases that you could run into. When you apply the ratio test to the power series, if you get 0, then that tells you that the series converges for all x, and the radius of convergence is infinity, and your interval of convergence goes from -infinity to infinity. If the limit of as n goes to infinity when you apply the ratio test goes to infinity, then this means that your series only converges at the center, and your radius of convergence is equal to 0. And then the third case, which is the most common, is when you wind up with something like this here, then you're going to have 1 over the radius of convergence times x minus the center and absolute value less than 1. When you wind up with something like this, your interval of convergence goes from -r plus c to r plus c, but this needs to be investigated. You have to check each endpoint. So first up here, we're going to find the interval of convergence of this power series. And the first thing I note here is we're just going to say a sub n is equal to -1 to the n, x to the n, over n squared plus 2. So for something like this, the first thing that I notice is that the center of the power series is going to be at 0, because that's the x value that would make everything equal 0 for all terms starting from n equals 1 going to infinity. But now the technique involved is we have to apply the ratio test. So to apply the ratio test, we're taking the limit as n goes to infinity of the a sub n plus 1 term divided by the a sub n term. So the a sub n plus 1 term, we're just going to replace each of those n's with an n plus 1, and that's going to give us this expression here. And now just a little bit of a shortcut is when we're applying the ratio test, when you're doing a sub n plus 1, that's this expression here that I just wrote, and you're dividing by a sub n, dividing by a sub n is the same thing as multiplying by its reciprocal. So I just like to just jump right in at this step, because for these questions, there's a lot of stuff you have to write. So now this is equal to the limit as n goes to infinity, and now we just simplify things a bit. X to the n plus 1 over x to the n, this is going to cancel out and leave us with a power of 1, because n plus 1 is exactly 1 more than n. And now here, -1 to the n plus 1 over -1 to the n, this is gone, and we're going to be left with a power of 1. And then after this, what we could do is we could simplify this. And one thing I like to do is notice the absolute value of -1 is just 1, so we could just leave that behind. But the absolute value of x could be anything right now, so it has to stay behind in the absolute value. Now n is going to infinity, so n squared plus 2 is going to be positive, so we could take it out of the absolute value. And also this expression on bottom we could expand. N plus 1 squared is n squared plus 2n plus 1, and then we just tack on that plus 2 at the end. And just know, when you're taking limits at infinity, what we have here is we're taking the limit as n goes to infinity, which means that we're going to focus on the leading terms here, which are n squared and n squared. So now this is going to simplify. What we're going to have is we're going to have absolute value of x times the limit as n goes to infinity of this expression. Since our leading terms have matching powers, the limit is equal to the ratio of the coefficients, so it's going to be equal to 1. And remember, from the ratio test, we're going to set that whole limit to be less than 1. And what this tells us is we have absolute value of x is less than 1. And now from here, what we could say is that x is between -1 and 1. Now the question is only asking us to find the interval of convergence, but if our center is at 0 and we're going from -1 to 1, that tells us the radius of convergence is equal to 1. So this is not necessary to find, but we could write it in anyway. So now for the next stage of this problem, this is incomplete. We have to check the endpoints of our interval. So we're going to have to evaluate our series at x equals -1. And if we plug in x equals -1 to the original series, that's going to give us the series from n equals 1 to infinity. We'll have -1 to the n times, and then we'll have -1 to the n power like this. And this is going to be over n squared plus 2. And if we simplify this, now what we have is the series from n equals 1 to infinity. And my thought process here, this I'll just simplify in my head, is that when we do -1 to the n times -1 to the n, law of exponents says that we add n plus n, which is going to give us 2n, and that's a number that's always even. So since n is an integer, n is a whole number, so -1 to an even power is just equal to +1. So now I could just simplify this as 1 over n squared plus 2. And then what we could say from here is that this series converges. And since this series converges, that means that x equals -1 is included in the interval of convergence. If we needed to come up with a reason for why this series converges, it's kind of lazy to just say p series because of that plus 2 at the end, but we could use the limit comparison test, which we'll abbreviate. We'll use the limit comparison test with the series from n equals 1 to infinity of 1 over n squared, where this is a convergent p series. So far we have x equals -1 is included in our interval. So now we'll check the other endpoint. We'll have x equals +1. And if we remember the series started out, we have n equals 1 to infinity, and it was -1 to the n, and then it was x to the n power. So now we have 1 to the n power over n squared plus 2. And this series will simplify if we work this out. -1 to the n times 1 to the n is just going to give us -1 to the n on top over n squared plus 2. And notice what we have here. We have another series that converges. This series converges, and if we had to use a convergence test for this, we could use the alternating series test. So since this series converges at x equals 1, we can include that in our endpoint, and now we could write out our interval of convergence is going to go from -1 to 1 inclusive. So same process here, we're going to apply the ratio test, and let's just say here this is the a sub n term. So we're taking the limit as n goes to infinity, and a sub n plus 1 is going to give us -1, and we'll have m plus 1 plus 1, which is going to give us m plus 2, and then we're going to have x minus 3 to the m plus 1 power over, we'll have 5 to the m plus 1 times the square root of m plus 1. So once again, this is our a sub n plus 1, and when we do the limit as n goes to infinity of a sub n plus 1 divided by a sub n, the shortcut is instead of dividing by this fraction, we'll just multiply by the reciprocal, which is going to give us 5 to the n radical n over 5 to the n plus 1 x minus 3 to the n. So now at this step we just have a little bit of algebra to do. Notice here x minus 3 to the n plus 1 over x minus 3 to the n. This is going to cancel out and leave us with a power of 1. -1 to the n plus 1 goes away completely, and we have a leftover power of 1 on top. 5 to the n goes away completely, and we're left with a power of 1 on bottom like this. And now what we could do is we could just simplify this a little bit. This is the limit as n goes to infinity. The absolute value of -1 is 1, so we could just forget about that. The absolute value of x minus 3, we're just going to write as the absolute value of x minus 3. And what we have here, the absolute value of 5 to the first, we could just write on bottom as 5. And now we have times the leftovers inside the absolute value was square root of n over, and on bottom we're left with square root of n plus 1. We already took the 5 that was left here and wrote it under the absolute value of x minus 3. So once again, I don't need absolute value around this because n is going to infinity, so these are both positive expressions. So we can get rid of the absolute value. But now we're taking the limit as n goes to infinity, and notice the leading terms inside both of these radicals are matching, which means this limit of this part is going to go to 1. So this is going to be equal to the absolute value of x minus 3 over 5 times 1, or I could just say like this. And now when we're done with the ratio test, we set it to be less than 1. So now what we're going to do is we have to solve for x. So we got to do a little bit of algebra. We're going to multiply both sides by 5, and that tells us the absolute value of x minus 3 is less than 5. And now if we start to write things out, remember the center of our series is going to be at 3 because that's the x value that makes everything 0. The radius of convergence at this step is going to be obvious that it's equal to 5. And now that's going to help us build our preliminary interval before we explore the endpoints. So now we could say x minus 3 is between negative 5 and 5. And now just add 3 to all three sides. And this is going to give us, we're going to have negative 2 is less than x, which is less than 8. But now we have to check out the endpoints. So let's explore the first endpoint at x equals negative 2. So if we plug in x equals negative 2 to the series, we're going to have the series from n equals 1 to infinity, and we're going to have negative 1 to the n plus 1. But now we're replacing x with negative 2, and that's going to give us negative 2 minus 3, which is negative 5 to the n power over, and we're going to have 5 to the n power on bottom times the square root of n. So now we just have to do a little bit of algebra here. And what I notice right away is these two terms. Negative 5 to the n over 5 to the n. Just know anytime you have something like a to the c over b to the c, you could call this a over b to the c power. So that's the technique I want to use here. So far we have negative 1 to the n plus 1, but if we use this rule of algebra, negative 5 divided by the base 5 here is going to give us negative 1 to the n power, and we're dividing by root n. But now this is where we have to think very carefully. When you multiply the numerator across, so we have negative 1 to the n plus 1 times negative 1 to the n, you're going to use law of exponents. When you add those, n plus 1 plus n is 2n plus 1, and that is always odd. So this is odd, which tells us we have negative 1 to an odd power, we're going to have just negative 1 on top. So this is going to be negative 1 over root n, and if we factor out that negative, this is negative 1 times the series from n equals 1 to infinity of 1 over n to the 1/2 power. And this is a divergent p-series. So this series diverges. And how do we know? Because it's a p-series where the exponent 1/2 is less than or equal to 1. So this is not going to be included in our interval of convergence. X equals negative 2 is not part of the interval. One small detail, that negative 1 in front, we could also mention in our explanation that it's a p-series times the constant negative 1. So now we got to check the other endpoint. So we plug in x equals 8. And when we replace x with 8, we're going to have the series from n equals 1 to infinity. We have negative 1 to the n plus 1. And now plug in x equals 8, and that's going to give us 8 minus 3, which is going to give us 5 to the n power on top. And on bottom, we have 5 to the n times square root n. So this time around, 5 to the n just cancels out nice and cleanly. And we're going to be left with this in our series. So we have the series from n equals 1 to infinity of negative 1 to the n plus 1 over the square root of n. So this time around, this is different because this is an alternating series. And the non-negative part, 1 over square root n, is positive, decreasing, and the limit as n goes to infinity of 1 over root n goes to 0. So by the alternating series test, this series converges. So we're just abbreviating here. This series converges by the alternating series test. So now we could write out our interval of convergence. Our series diverged at x equals negative 2, and it converged at x equals 8. So our interval of convergence is going to be open at the endpoint negative 2, but closed at x equals 8. So question 3, we have this power series, and we're going to start by using the ratio test. So we have the limit as n goes to infinity. Remember, this is our a sub n term, the starting term in our series. So we're taking the limit as n goes to infinity of a sub n plus 1, which is going to give us ex to the n plus 1 over, and we'll have natural log, and if we replace n with n plus 1, we'll have n plus 1 plus 1, which is going to give us n plus 2. So remember, we're doing, this is a sub n plus 1, and we're dividing by a sub n, which is the same thing as multiplying by its reciprocal. So that's going to bring us to this step here. And now what we have from this step is we could do a little bit of algebra. So ex to the n plus 1 over ex to the n, this is going to go away completely, and it's going to leave us with an exponent of 1. So then in the next line, we're going to have the limit as n goes to infinity, and the absolute value of e is just e. So we're going to have e times the absolute value of x has to stay behind in the absolute value, because if x is positive or negative, we can't just get rid of that absolute value. And then the absolute value of natural log n plus 1 can pop out, because natural log of n plus 1 is going to be positive because we have n going from 1 to infinity. And we have natural log n plus 1 over natural log n plus 2 this could also exit the absolute value for the same reasoning. So now we get to this step, and we can't just plug in n equals infinity, because we'll have infinity over infinity, which is indeterminate. So in this case here, we would actually have to use L'Hopital's rule to evaluate this limit. So we could say that this is equal to e times the absolute value of x, and this is, once again, we're using L'Hopital's rule, and we have the limit as n goes to infinity, and now the derivative of natural log n plus 1 with respect to n is 1 over n plus 1. And then the derivative of the bottom term is going to be 1 over n plus 2. Okay, we could skip the chain rule here because the derivative of the inside is 1. And now if we simplify this, this is e times absolute value x, and we have the limit as n goes to infinity, and then we rearrange this, it'll rearrange to n plus 2 over n plus 1. And now this is a limit we could find because we have n plus 2 over n plus 1. The leading terms are matching. They have matching exponents, and their coefficients are both equal to 1. So the limit of this expression is going to be 1. So this will be e times absolute value x, and we're going to set this all to be less than 1. So now what we have here, if we go through the notes from before, our center of our power series is at 0. And now this part here tells us that if we do the algebra, the absolute value of x is less than 1 divided by e, after we divide both sides by e, which tells us our radius of convergence is equal to 1 over e. And now this gives us a preliminary interval that for right now, x is going to be between negative 1 over e and positive 1 over e, but now we have to check the endpoints. So let's check out the first endpoint, x equals negative 1 over e. If we plug this into our original series, we're going to have the series from n equals 1 to infinity. And if we do e times negative 1 over e, that's going to give us negative 1 to the n power on top over, and we'll have natural log of n plus 1 on bottom. Now, my thought process here, right away, I'm going to say that this series converges by the alternating series test, which we're going to abbreviate with AST here. And the thought process, the way that I know this, is I look at the non-negative part, 1 over ln n plus 1. So just this on its own is positive. This sequence of terms will be decreasing, and the limit as n goes to infinity of this expression here will go to 0. So that tells us the alternating series test does apply and tells us this series does converge. And now the next thing we would have to do is check out x equals positive 1 over e. However, when we plug in x equals positive 1 over e to the original series, we're going to have e times positive 1 over e, which gives us 1 to the n, which is just going to give us 1 over ln n plus 1. And this series, we could say here, diverges. And this one, I would use the direct comparison test. So we're not going to write the most rigorous explanation for all of these little tests here, like testing the endpoints. But the thought process, how do I know that 1 over ln n plus 1, that's going to diverge, is I would compare this to the function y equals x. So if I looked at y equals x, and I think about y equals natural log of x plus 1, if you look at those two together, y equals x just goes like this, and y equals natural log of x plus 1 would have a vertical asymptote at x equals negative 1, and the function would look something like this. So it would go through the point 0, 0, because when x equals 0, you would have natural log of 1, which is 0. And this is what your function would look like. So notice, if I color code this a little better, y equals x is always above natural log of x plus 1. So if x is always greater than natural log x plus 1, then that means that 1 over x is always going to be strictly less than 1 over natural log of x plus 1, especially if we're considering x is greater than or equal to 1. So why does that help us here for direct comparison test? Well, if we do a direct comparison and we compare to the series, let's say we consider this series here from n equals 1 to infinity of just 1 over n, if this smaller series diverges, then every series bigger than it is also going to diverge. So that's how we would argue why this series diverges, and this is going to help us write out our final interval of convergence. So our interval of convergence is going to be closed at negative 1 over e, and it's going to be open at 1 over e like this. So for this last example here, we're going to use the ratio test again, and we have the limit as n goes to infinity. This is a sub n. So a sub n plus 1, we could say, is n plus 1 to the n plus 1 times x to the n plus 1 over, and then we have e to the n plus 1 times, and then where this is once again a sub n plus 1. When we divide by a sub n, we could multiply by the reciprocal, and we have e to the n power over n to the n times x to the n like this. So now at this step, what we could do is we just do a little bit of algebra, and we're going to use this idea in a moment, that a to the c over b to the c is equal to a over b to the c power. But we do the algebra. X to the n plus 1 over x to the n will simplify to x to the first on top, and then e to the n cancels out completely, leaving us with e to the first on bottom. So now we could do a little bit more algebra. Since the limit is as n is going to infinity, we could take the absolute value of x out. We're dividing by the absolute value of e, which is just e, and now we have the limit as n goes to infinity, and all the terms with an n have to stay behind. And one thing I want to do is rewrite this a little bit different. I'm going to rewrite that as m plus 1 times m plus 1 to the n, because if we were to multiply those two, it would bring us back to m plus 1 to the n plus 1. And now we're dividing by n to the n on bottom. And once again, the terms with the n could leave the absolute value because n is going to infinity. So these are all positive terms. So now we'll just group this a little bit different. This is equal to the absolute value of x over e times the limit as n goes to infinity of, we have m plus 1 times, and then this we would say is m plus 1 over n to the n power. Now the limit as n goes to infinity of this expression, this is 1 plus 1 over n to the n is going to work out to e, but the limit as n goes to infinity of this is going to go to infinity. So we're going to have infinity times absolute value of x over e. Now one thing to point out is that absolute value of x is going to be greater than or equal to 0. And let's say here, if we look at this power series, the center is at x equals 0, because that would make everything 0. So if x is anything but 0, this limit here is going to go to infinity. And we'll say here, for when x is non-zero. And this is one of the cases that we had in the notes before, that when this happens, that our interval of convergence is just going to be the center of the series.